We build rockets, send probes to the farthest corners of our solar system, and gaze deep into space with telescopes that reveal galaxies billions of light years away. Our technology is powerful, our curiosity boundless. Yet, no matter how far we venture, there are places we can never reach, realms so distant, so impossibly out of reach, that they will forever remain a mystery. These are the forbidden zones, regions lost to the relentless expansion of the cosmos, receding faster than the speed of light, slipping beyond the horizon of possibility. Some are buried within the event horizons of black holes, where gravity distorts time and space beyond recognition, sealing away whatever falls inside. Others exist in the earliest moments of the universe, hidden behind a veil of time, so thick that no telescope, no breakthrough, no future technology will ever pierce it. And yet, we wonder. We imagine. We reach with our minds where our bodies and machines cannot go. Could distant, unreachable galaxies harbor civilizations forever cut off from us? Do black holes conceal secrets about the fabric of reality itself? Is the birth of time locked behind an impenetrable cosmic curtain? The forbidden zones remind us of our limits, but they also ignite our greatest strength, curiosity. Even in the face of the unreachable, we ask, we explore, we dream. And perhaps, in doing so, we find something just as profound as the answers we seek. The universe is vast, far beyond what human eyes or even the most powerful telescopes can see. When we gaze at the night sky, we are peering back in time, looking at light that has traveled for billions of years to reach us. Yet, there is a limit, a cosmic horizon, beyond which we can never see, never explore, and never reach. This is the cosmic censorship zone, the region of the cosmos that exists beyond the observable universe, where reality itself becomes unknowable. The observable universe stretches out for about 46 billion light years in all directions. This might seem strange because the universe itself is only 13.8 billion years old. Shouldn't we only be able to see objects within a 13.8 billion light-year radius? The reason we can see farther is that space itself has been expanding all this time, stretching the fabric of reality and carrying distant galaxies away from us. Because of this expansion, light from the early universe has been redshifted, its wavelengths stretched as space itself grows, making it detectable today, even though the original objects are now far beyond their initial positions. But there is a fundamental problem with this expansion. It is accelerating. Due to a mysterious force known as dark energy, the universe is not just growing, but growing at an ever-increasing rate. This means that as time passes, more and more galaxies are slipping beyond our cosmic horizon, moving so fast that their light will never be able to reach us. Anything currently beyond 46 billion light years is forever lost to us, not because it doesn't exist, but because the very fabric of space is carrying it away faster than the speed of light can compensate. The idea of a cosmic censorship zone is an unsettling one. It suggests that there are parts of the universe, that will forever remain hidden, places where galaxies, stars, and perhaps even other civilizations exist, but we will never know about them. This is not just a temporary problem. Once something crosses this boundary, it is gone from our observable reality forever. It will never be possible for us to receive information, light, or any signal from beyond this limit. Even if humanity one day masters interstellar travel, even if we create spacecraft capable of approaching the speed of light, we will still never reach these hidden regions. The laws of physics themselves prevent us. This leads to a profound question: what lies beyond the observable universe? The simplest answer, according to the cosmological principle, is that the universe beyond our view looks much the same as the part we can see. If space is truly infinite, then galaxies, stars, and planets likely continue on endlessly beyond our cosmic horizon. The same fundamental laws of physics should apply, meaning that beyond our reach, similar processes of star formation, planetary evolution, and even life might be occurring. But there are other possibilities, ones that challenge our very understanding of reality. Some cosmologists suggest that beyond our observable universe, the very nature of physics might be different. If the Big Bang was not a single event, but one of many in an eternal inflation process, then the universe beyond our sight could be radically different. There could be entire regions where the constants of physics, such as the strength of gravity, the behavior of light, or even the nature of matter, are entirely unlike what we know. These would be separate pocket universes within a greater multiverse, forever cut off from our own. There is also the question of whether our own universe is finite or infinite. If the universe is truly infinite, then beyond our cosmic horizon, space continues without end, filled with infinite variations of galaxies and even perhaps versions of ourselves. In an infinite universe, every possible arrangement of particles must eventually repeat, meaning that somewhere beyond the cosmic censorship zone, an almost identical version of Earth could exist, with people almost exactly like us living their own lives, unaware of our existence. If the universe is finite, however, then what lies beyond the observable universe could be something much stranger. There could be a physical boundary, a literal edge to space, although this idea is difficult to reconcile with modern physics. More likely, if the universe has a finite shape, it could wrap around itself in ways we cannot yet understand. Traveling far enough in one direction might eventually bring you back to where you started, like moving on the surface of a sphere. And then there is the possibility that beyond our observable universe, there is simply nothing. If space itself has an end, then past that limit, there might be a true void, a region where even space and time cease to exist. But this idea contradicts much of what we understand about physics, as empty space itself still has properties such as quantum fluctuations and vacuum energy. What makes the cosmic censorship zone so eerie is that we will never know for sure. As the universe expands, the region of space we can access shrinks in relative terms. Galaxies we can see today will eventually fade from view, their light stretched so far into the redshift that they become undetectable. Eventually, Billions of years from now, our observable universe may shrink down to just the few galaxies closest to us, with all others lost forever. This means that the universe we perceive is a fleeting, temporary window into a much larger reality. Future civilizations might find themselves in a cosmos that appears far smaller, where the grand cosmic web of galaxies has vanished into the darkness, leaving only a small cluster of celestial bodies. The knowledge we have now, that we live in a vast, expanding cosmos filled with billions of galaxies, could become lost, buried in history, with no way to verify it. Yet, even within this limitation, our universe holds profound mysteries. The cosmic censorship zone is not just a boundary, it is a reminder of the limits of human knowledge. It tells us that no matter how far we look, there will always be something just beyond our reach, some deeper truth that we can never fully grasp. It is the ultimate cosmic horizon, the final frontier that can never be crossed, not because we lack the technology, but because the very nature of reality ensures that some things will forever remain hidden. This is a humbling realization. We are used to thinking of science as a tool that can unlock all mysteries, that with enough effort, we can understand anything. But the nature of the expanding universe means that some answers will always be out of reach. This does not mean we should stop searching. On the contrary, it makes our quest for knowledge all the more precious. Every moment we have to study the cosmos, every piece of information we gather, is a fleeting opportunity before the universe moves beyond our grasp. In the end, the cosmic censorship zone is not just a physical limit, it is a philosophical one. It forces us to confront the idea that we are small, temporary observers in an endless, shifting reality. It reminds us that there will always be things we cannot know, places we cannot visit, and mysteries we cannot solve. But perhaps that is what makes exploration so beautiful. The universe is not ours to fully understand, but it is ours to wonder about, to question, and to appreciate, even as it drifts further and further from our reach. The universe is a time machine. Every time we look up at the night sky, we are not seeing objects as they are in the present, but as they were in the past. The farther away a galaxy is, the further back in time we are looking. Some galaxies are so distant that the light we see from them today has been traveling for billions of years. And here lies one of the most haunting truths about the cosmos. Some of the galaxies we observe in the night sky no longer exist. They are phantoms, cosmic ghosts whose last light is only just reaching us, while they themselves have already disappeared into the void. This eerie phenomenon happens because of the universe's rapid expansion. Space itself is stretching, pushing galaxies farther apart. For nearby galaxies, this expansion is slow enough that we can still see and interact with them. But for galaxies at extreme distances, the expansion is happening so quickly that they are effectively being pulled out of our observable universe. This means that while we can still see the light they emitted billions of years ago, They have already crossed what scientists call the cosmic event horizon, the point beyond which no information, not even light, can ever reach us again. To truly grasp this idea, imagine a boat on the ocean, drifting toward the horizon. From the shore, you watch as it moves farther and farther away. Eventually, it reaches a point where it disappears from view, not because it has ceased to exist, but because the curvature of the Earth prevents you from seeing it. Now, replace the ocean with space and the boat with an entire galaxy. The universe is stretching so rapidly that certain galaxies have already moved beyond our cosmic horizon, never to be seen again. Their light is still traveling toward us, but once it has all arrived, no more will follow. They will fade from view, not because they have become dim, but because they are too far away for their light to ever reach us again. The most astonishing aspect of this phenomenon is that there are galaxies we can see today in our telescopes that have already ceased to exist. Some of them may have been swallowed by black holes. Others might have been torn apart in colossal collisions, and many have simply been stretched out into nothingness by the relentless expansion of space. The light we receive from them today is their final message, their last glimpse into existence before they vanish forever. One of the most famous examples of this is the Hubble Deep Field Image, which captured thousands of distant galaxies in a single frame. Many of these galaxies are so far away that their light has been traveling for over 10 billion years to reach us. Some of them existed when the universe was in its infancy, just a few 100 million years old. And yet, they are no longer there. The structures they formed, the stars they contained, and perhaps even the planets that orbited within them are all gone. But their light, like an echo from the past, is only just now reaching us, allowing us to witness them as they were, frozen in time. This concept is difficult to wrap our minds around because, in our everyday experience, things do not just disappear like this. When we look at an object, we expect it to exist in the present moment. But the universe does not work that way. The farther away something is, the older the image we see of it. For extremely distant galaxies, we are looking so far back in time that their present state is unknowable. Some may still exist in some form, but others are simply gone, their matter dispersed, their energy absorbed into the vastness of space. What makes this even more unsettling is that the universe's acceleration is irreversible. Galaxies that are on the edge of our observable universe today will soon be lost forever. We will still see their light for a while, perhaps millions or even billions of years, but that light will eventually stop coming. They will fade into blackness, not because they have been destroyed, but because the laws of physics make it impossible for their photons to reach us. The fabric of space will have stretched so much that they will have effectively been erased from our reality. This means that, in a way, we are living in a golden age of cosmic observation. Right now, we have the technology to look deep into space and see the remnants of ancient galaxies. But in the far future, observers in our galaxy will see a much lonelier universe. The distant galaxies we marvel at today will no longer be visible. The Milky Way and its neighboring galaxies will be all that remains in sight, and future astronomers might never know that billions of other galaxies once existed. The record of their existence will be lost, their light no longer able to reach us. But this does not mean that these phantom galaxies are meaningless. Even though they have disappeared from the present universe, their light tells us a story of the early cosmos, of the first stars and galaxies forming, of the evolution of structure in the universe. Every photon that reaches us is a message from the past, a whisper from a galaxy that may have been long gone. These photons are precious because they allow us to piece together the history of the universe before it is lost to time. There is also a profound philosophical question hidden within this reality. If we see something, but it no longer exists, did it ever really exist in the way we understand existence? When we look at a galaxy 10 billion light years away, we are seeing it as it was 10 billion years ago. But if we could somehow instantly teleport there, we would find nothing. The stars would be gone, the structures changed beyond recognition. We would be staring at empty space, or at something entirely different from what we expected. This challenges our understanding of what now really means in a universe where time and space are deeply connected. It also raises another question: how much of our own universe has already disappeared? Just as we see ancient galaxies that no longer exist, there could be civilizations in distant parts of the cosmos looking back at the Milky Way as it was billions of years ago. To them, our galaxy might be nothing more than a faint glimmer from a time long past, a relic of a universe that has moved on without us. One day, we too may become a phantom, a galaxy whose light continues to travel outward even as we fade from existence. The universe is a vast and mysterious place, and the phantom galaxies that haunt our telescopes are a reminder that nothing is permanent. Everything we see is temporary, a flickering moment in cosmic history. And yet, in that fleeting moment, there is beauty. The knowledge that we are witnessing something that no longer exists makes every image, every observation, all the more precious. It reminds us that the universe is always changing, always evolving, and that we are lucky to glimpse even the tiniest fraction of its story before it, too, fades beyond our reach. The universe hides its deepest mysteries in darkness. Among the strangest of these mysteries is the idea of primordial black holes, hypothetical remnants from the earliest moments after the Big Bang. If they exist, they are not like the black holes we know, the ones that form from the deaths of massive stars. These would be different, formed not from collapsing stars, but from the extreme density fluctuations in the newborn universe. But here's the paradox. If they exist, they are so elusive, so small, and so perfectly hidden in the fabric of space that we may never find them. Primordial black holes are believed to have formed just fractions of a second after the universe came into existence. At that time, the cosmos was an unimaginably hot and dense place, a chaotic sea of energy and particles. Tiny quantum fluctuations, slight imbalances in density, could have been enough to collapse regions of space into minuscule black holes. Unlike the ones formed by dying stars, these black holes could be as small as an atom or as massive as a planet, depending on the density of the region they formed in. Theoretically, primordial black holes could have survived for billions of years, drifting through the cosmos as invisible relics of the early universe. But their size makes them nearly impossible to detect. Unlike stellar mass or supermassive black holes, which are surrounded by glowing accretion disks of matter being pulled in, primordial black holes would be mostly isolated, wandering through the universe like silent ghosts. If they are small enough, they would emit radiation and slowly evaporate over time due to a process known as Hawking radiation. But if they are just a little larger, they could persist indefinitely, completely invisible to our current technology. For decades, scientists have searched for evidence of these ancient black holes, but finding them is like looking for a grain of sand in an infinite desert. They do not emit light. They do not interact with their surroundings in any obvious way, and they may be far too small to influence nearby objects significantly. The only hope of detecting them lies in their gravitational effects, perhaps bending the light of distant stars as they pass in front of them, or subtly affecting the movement of cosmic structures. Yet even these clues are faint, almost imperceptible against the vastness of space. One of the most intriguing ideas about primordial black holes is that they could be a candidate for dark matter, the invisible substance that makes up most of the mass in the universe. Dark matter is known only through its gravitational influence. It has weight, it pulls on galaxies, but it emits no light, no radiation. Could primordial black holes be the hidden mass that has eluded scientists for so long? Some researchers believe it is possible, but there is no direct evidence. If primordial black holes are indeed the source of dark matter, then they are even more elusive than we imagined. They are everywhere, yet they remain unseen. The frustrating reality is that even if they do exist, we may never be able to prove it. They are too small to be observed directly, too dark to emit detectable radiation, and too isolated to reveal themselves through interactions. Even the most advanced telescopes and gravitational wave detectors may not be enough to confirm their presence. We might only ever be able to infer their existence from indirect clues, subtle changes in the motion of galaxies, brief flashes of light as they pass in front of distant stars, or tiny distortions in the cosmic microwave background left over from the Big Bang. There's a cruel irony in this. The very nature of primordial black holes makes them one of the most compelling ideas in modern physics, yet at the same time, they may be forever beyond our reach. They could be everywhere, hidden in the void, yet we might never be able to prove they are real. The universe does not always reveal its secrets easily. Some questions may remain unanswered, not because they have no answers, but because the answers are too well hidden for us to ever find. And yet, the possibility of primordial black holes continues to haunt us. If they do exist, then they are the oldest structures in the universe, predating galaxies, stars, and even atoms. They are remnants of a time before anything we recognize existed. And if they don't exist, then we are left with another mystery. What happened to the density fluctuations that should have formed them? Why did the universe evolve in such a way that it avoided their creation? Either way, whether they are out there or not, the search for primordial black holes forces us to confront the limits of what we can know. The universe is vast, and some of its secrets may remain hidden forever, lost in the silence of space. The solar system we see today is a product of billions of years of evolution, shaped by violent collisions, planetary migrations, and the relentless pull of gravity. When we look at the moon in the night sky, or observe the moons of Jupiter and Saturn through telescopes, we are only seeing a fraction of what once existed. The solar system was not always as it is now. It was once a chaotic, dynamic place where countless moons formed, only to be torn apart, ejected into deep space, or lost to the void forever. These lost moons, remnants of a time when the solar system was still young and unstable, may still exist somewhere, hidden beyond our reach, drifting alone in the darkness. Some may have been destroyed in violent impacts, their shattered remains now part of asteroid fields or planetary rings. Others may have been thrown into the distant Oort cloud, a vast, icy region at the edge of the solar system, where they would remain frozen, undisturbed, and nearly impossible to detect. And some may have escaped entirely, becoming rogue moons wandering the galaxy, untethered from any star, destined to drift endlessly through interstellar space. In the earliest days of the solar system, more than 4.5 billion years ago, there were no clearly defined planets, no stable orbits, and no predictable patterns. Instead, there was a swirling disk of dust, gas, and debris surrounding the young sun, slowly coalescing into larger bodies. As this material clumped together, the first planets and their moons began to form. But this was not a peaceful process. Immense collisions were common as newly formed planets and moons smashed into each other, reshaping their surfaces or destroying them entirely. Some of these impacts were so powerful that they changed the course of the entire solar system. The moon we see today is thought to have formed from such an event, a massive collision between the early Earth and a Mars-sized body, which ejected debris into orbit that eventually coalesced into our moon. If this could happen to Earth, then it is likely that other planets also had moons that were formed, destroyed, and replaced multiple times throughout history. The giant planets, Jupiter and Saturn, have dozens of moons today, but in the past, they may have had even more. These gas giants are so massive that they have the gravitational power to capture passing objects, meaning that many of their moons were likely stolen from the asteroid belt or even from other planets. But just as they can capture moons, they can also lose them. When planets migrate, shifting their positions in the solar system due to gravitational interactions, they disrupt everything around them. A moon that was once in a stable orbit can suddenly find itself in a highly elliptical path, leading it to collide with another moon, crash into its host planet, or be ejected from the solar system entirely. Jupiter and Saturn likely underwent significant migration early in their histories, meaning that many of their original moons may have been lost in the process. Some moons may still be out there, hiding in the farthest reaches of the solar system, beyond the Kuiper Belt, in the Oort cloud. The Oort cloud, is a mysterious, distant region that lies nearly a light year away from the Sun, filled with icy bodies that are thought to be remnants of the early solar system. It is believed to be the source of long-period comets, objects that occasionally get disturbed and fall toward the inner solar system. If smaller bodies, like comets, can survive in the Oort cloud for billions of years, then it is possible that some lost moons also ended up there, trapped in the gravitational influence of the Sun, but too far away to be seen. These moons would be frozen and lifeless, locked in deep space, moving so slowly that their presence would be almost undetectable. Even if they exist, finding them would be nearly impossible with current technology, as they would be too dark and too distant to observe directly. Other moons may have faced a more dramatic fate: complete ejection from the solar system. If a moon was thrown outward with enough force, it could have escaped the Sun's gravity entirely and become a rogue object drifting freely through the galaxy. Scientists have already discovered rogue planets, planets that do not orbit any star, but instead move through space alone. If rogue planets exist, then rogue moons must exist as well. Some of them may have once been part of our own solar system, but now they wander the Milky Way, unseen and untethered to any world. Without a nearby star to illuminate them, these lost moons would be invisible, impossible to detect with even the most advanced telescopes. They could pass by other solar systems, moving silently through the darkness, never captured by another planet's gravity, forever alone. If these moons once had water, subsurface oceans, or even the conditions necessary for life, their ejection into deep space would have sealed their fate. Without the warmth of a star, any potential life would have been frozen in an instant, preserved in the icy shell of a moon that would never see light again. The thought of such worlds, places that once held the potential for oceans, weather, and geological activity, now drifting aimlessly through the void, is a haunting reminder of how fragile celestial bodies can be. Unlike planets, which have strong gravitational holds on their orbits, moons are more easily lost, making them some of the most transient objects in the universe. The lost moons of the early solar system are not just a relic of the past. They are a key to understanding how planetary systems form and evolve. By studying the moons that remain, scientists can infer what might have happened to those that were lost. The craters on existing moons, the irregular shapes of asteroid belts, and the chaotic orbits of small bodies in the outer solar system all contain clues to a history that is largely invisible. If we ever develop the ability to send spacecraft to explore the Oort cloud, we may find evidence of these lost moons, perhaps even remnants of worlds that were once part of our own neighborhood. But for now, these lost moons remain a mystery, hidden beyond our reach. Some may be orbiting unnoticed in the vastness of space. Some may be buried in the distant corners of the solar system, and others may have left us forever, drifting alone in the emptiness between the stars. We may never know their names, their shapes, or their stories. But their absence is a reminder of the impermanence of celestial bodies, the way the cosmos is constantly shifting, changing, and reshaping itself. The universe is full of forgotten worlds, and among them are the lost moons, silent travelers, unseen and unremembered, but forever part of the story of our solar system. The universe is in constant motion, a vast and dynamic expanse where galaxies drift through space, bound together by gravity. Our own Milky Way, along with countless other galaxies in the local universe, is not simply floating aimlessly. It is being pulled towards something massive and mysterious. This unseen force is known as the Great Attractor, a gravitational anomaly so powerful that it is drawing entire galaxy clusters toward it at immense speeds. And yet, despite its influence, we cannot see it directly. The Great Attractor lies hidden behind the thick veil of our own galaxy, in a region known as the Zone of Avoidance, making it one of the greatest mysteries of modern cosmology. To understand the significance of the Great Attractor, we first have to look at the large-scale structure of the universe. Galaxies are not evenly distributed throughout space. Instead, they form vast cosmic webs with dense clusters connected by filaments of galaxies, separated by enormous voids. Our Milky Way belongs to a local collection of galaxies known as the Local Group, which itself is part of a much larger structure called the Laniakea supercluster. This supercluster contains over 100,000 galaxies, all gravitationally bound and moving in the same general direction. That direction, as astronomers have discovered, leads toward the Great Attractor. The Great Attractor's pull is enormous. Our galaxy is speeding toward it at about 600 kilometers per second, more than 1.3 million miles per hour. Everything in our cosmic neighborhood, including the entire Virgo cluster and other nearby galaxy groups, is moving in the same direction. This suggests the presence of an enormous mass, far larger than anything in our immediate vicinity. And yet, when astronomers try to pinpoint the source of this immense pull, they run into a problem. It is located in a part of the sky that is obscured by the dense clouds of gas, dust, and stars in the Milky Way. This region, known as the Zone of Avoidance, blocks our view, making direct observations impossible with visible light. For decades, scientists have struggled to understand what lies beyond this cosmic barrier. If the Great Attractor is so massive that it can influence the movement of entire galaxy clusters, why can't we see it? The answer lies in the way galaxies are distributed. Unlike a single object, such as a black hole or a planet, the Great Attractor is not one compact body, but rather a dense region of space filled with galaxies and dark matter. The combined gravitational pull of these structures is what creates the attraction. However, because the Great Attractor spans such a vast region, it does not emit concentrated light like a star would, making it even more difficult to detect. Despite the challenges, astronomers have found ways to study the Great Attractor indirectly. By using radio waves and X-ray telescopes, which can penetrate the dust and gas that block visible light, scientists have detected some of the galaxies and galaxy clusters within the region. These observations suggest that the Great Attractor is part of an even larger structure known as the Shapley supercluster, one of the most massive known concentrations of galaxies in the observable universe. The Shapley supercluster contains thousands of galaxies, and is thought to be the true source of the gravitational pull affecting our region of space. But the mystery does not end there. Even beyond the Shapley supercluster, astronomers have found evidence that our entire region of the universe is being influenced by an even more distant and powerful force. This has led to the discovery of what is known as the Dipole repeller, a vast void in the universe that is effectively pushing us away while the Great Attractor pulls us forward. The interplay between these massive structures suggests that the universe is shaped by even larger forces than we once thought, forces that extend far beyond what we can currently observe. One of the most intriguing aspects of the Great Attractor is the role of dark matter. Ordinary matter, the kind that makes up stars, planets, and galaxies, accounts for only a small fraction of the universe's total mass. The rest is composed of dark matter and dark energy, both of which remain largely mysterious. It is possible that the Great Attractor's immense pull is not just the result of visible galaxies, but also of vast amounts of unseen dark matter. If this is the case, then our inability to directly observe the Great Attractor is not just due to the Milky Way blocking our view, but also because much of its mass is made up of an invisible substance we still do not fully understand. As technology advances, astronomers are developing new ways to peer into the hidden corners of the universe. Infrared and radio telescopes continue to reveal glimpses of the galaxies within the zone of avoidance, while future space missions may offer even deeper insights. The Vera C. Rubin Observatory, set to begin operations in the coming years, will provide an unprecedented survey of the sky, potentially uncovering more clues about the Great Attractor's nature. Similarly, upcoming space telescopes like the James Webb Space Telescope's successors could help refine our understanding of this gravitational enigma. For now, the Great Attractor remains one of the most intriguing and elusive cosmic mysteries. We know it is there, we feel its pull, and yet we cannot fully see it. It is a reminder that, despite all the progress we have made in understanding the universe, there are still vast and powerful forces shaping our cosmic destiny that remain hidden from view. Perhaps one day, with the right tools and the right discoveries, we will finally unveil the true nature of the Great Attractor and its place in the grand structure of the cosmos. Until then, we continue to race toward it, bound by the invisible threads of gravity that weave the universe together. In the vast, mysterious cosmos, there are particles so elusive that they pass through entire planets, stars, and galaxies without leaving a trace. Among them are neutrinos, ghostly subatomic particles that barely interact with anything at all. But there may be an even stranger version of these particles, one that is so undetectable, so intangible that it could be all around us without us ever knowing. These are sterile neutrinos, the ghost particles of the universe, and if they exist, they may hold the key to some of the deepest mysteries of modern physics. To understand sterile neutrinos, we first need to look at their more familiar relatives, the three known types of neutrinos: electron, muon, and tau neutrinos. These neutrinos are produced in abundance throughout the universe, emerging from nuclear reactions in stars, supernovae, and even human-made experiments. Every second, trillions of neutrinos pass through your body without you ever noticing, because they interact so weakly with matter that they simply slip through atoms as if they weren't there. Even with this near invisibility, physicists have been able to detect and study these neutrinos using giant underground detectors filled with massive tanks of water or liquid argon, where the rarest of interactions leave behind a faint trace of their presence. But sterile neutrinos are different. Unlike the known types of neutrinos, which interact through the weak nuclear force, sterile neutrinos are theorized to not interact at all with ordinary matter, not even in the minimal way that regular neutrinos do. The only influence they have on the universe would be through gravity, meaning that even our most advanced neutrino detectors would be completely blind to them. If sterile neutrinos exist, they could be the most elusive form of matter in the universe, hidden in plain sight, yet forever beyond our reach. The idea of sterile neutrinos arises from several unresolved mysteries in physics. One of the biggest puzzles is why neutrinos have mass at all. In the standard model of particle physics, the framework that describes all known particles, neutrinos were originally thought to be massless. However, experiments have shown that neutrinos do have mass, though incredibly tiny. This discovery suggests that there might be physics beyond the standard model, and one explanation is the existence of additional neutrino types, sterile neutrinos that interact only through gravity. Another clue pointing to sterile neutrinos comes from anomalies in experimental data. Some neutrino experiments, such as the LSND experiment in the 1990S and the Mini-Boon experiment more recently, have observed unexpected results that cannot be easily explained by the three known neutrinos alone. If sterile neutrinos exist, they could also help solve the mystery of dark matter. Dark matter is one of the biggest unsolved problems in cosmology. It makes up about 27% of the universe, but it does not emit, absorb, or reflect light, making it completely invisible. Scientists only know it exists because of its gravitational effects on galaxies and cosmic structures. Some theories propose that sterile neutrinos could be a form of dark matter, explaining why it is so difficult to detect. Unlike traditional dark matter candidates, sterile neutrinos would be extremely light and could have shaped the early universe in ways we have yet to fully understand. The challenge, of course, is proving that sterile neutrinos exist, because they do not interact via the weak force, as regular neutrinos do. Our current detection methods are useless. Scientists have tried indirect approaches, looking for anomalies in neutrino oscillations, changes in neutrino types as they travel through space. If a neutrino transforms into a sterile neutrino and back, it could cause small distortions in experimental data, giving us a hint of its presence. Some ongoing experiments, such as the Ice Cube Neutrino Observatory in Antarctica and the upcoming DUNA Deep Underground Neutrino Experiment, are searching for such signatures, but so far, no definitive evidence has been found. The implications of discovering sterile neutrinos would be enormous. Not only would they force us to rewrite parts of the standard model, but they could also reshape our understanding of the universe's composition and evolution. They might even provide insights into why the universe contains more matter than antimatter. According to current physics, matter and antimatter should have been created in equal amounts during the Big Bang, which should have led to mutual annihilation, leaving behind only radiation. But since the universe is clearly filled with matter rather than antimatter, something must have tipped the balance. If sterile neutrinos played a role in this imbalance, they could be the missing link in one of the most fundamental questions in cosmology. But what if sterile neutrinos are never found? If they exist but are truly undetectable, they would remain forever beyond our reach, a ghostly presence influencing the cosmos in ways we may never directly observe. This would be one of the most frustrating possibilities in physics, a fundamental particle that shapes reality but can never be conclusively proven to exist. It would be like knowing that a hidden force controls the universe, but never being able to touch it, see it, or measure it in any way. And yet, history has shown that what seems undetectable today may become observable with new technology in the future. When the neutrino was first theorized in the 1930s, many physicists believed it would never be detected, as it was thought to interact too weakly with matter. Decades later, detectors were built that proved neutrinos were real. Perhaps one day, a breakthrough in physics will allow us to indirectly confirm the existence of sterile neutrinos, unlocking one of the final secrets of the cosmos. Until then, sterile neutrinos remain a tantalizing possibility, a whisper in the fabric of the universe, a silent force that may exist just beyond our grasp. Whether they are the key to dark matter, the answer to cosmic asymmetry, or merely a phantom prediction that leads us in new directions, their mystery continues to haunt the frontiers of modern physics. For as long as humans have gazed at the night sky, they have wondered where everything came from. The prevailing scientific theory is that the universe began 13.8 billion years ago in an event known as the Big Bang. Everything we see today, stars, galaxies, planets, and even time itself, was born from this moment of unimaginable energy and expansion. But this explanation raises a deeper question. What came before the Big Bang? Was there a time before time, or did everything simply emerge from nothing? And if the universe has always existed in some form, are all past versions of reality lost to us forever, erased like footprints on a cosmic shore? One of the most perplexing ideas in modern physics is that time itself may have begun with the Big Bang. According to Einstein's theory of general relativity, space and time are inseparable. They form the very fabric of the universe. If the universe had a beginning, then time itself must have had one too. This means that asking what came before the Big Bang might be like asking what is north of the North Pole. It may be a meaningless question. However, many physicists are not satisfied with this answer. If the universe came from nothing, what determined the laws of physics that govern it? Why does the universe exist at all, instead of simply remaining an empty void? These questions have led scientists to explore other possibilities, including the idea that the universe is eternal and has always existed in some form. One of the most popular alternative theories is the idea of a cyclic universe. Instead of beginning from absolute nothingness, the universe may go through an endless series of expansions and contractions, much like a cosmic heartbeat. In this model, the Big Bang was not the true beginning, but merely the latest rebirth of the universe. Before our universe, there may have been another universe that expanded, collapsed, and then gave rise to the one we inhabit today. If this process has been happening forever, then the universe has no true starting point, only endless cycles of creation and destruction. But if the universe is cyclical, what happened to all the previous universes? Why do we have no memory or evidence of them? The answer may lie in entropy, the tendency of the universe to move toward disorder over time. Each time the universe is reborn, the information from the previous cycle is lost. This means that even if infinite past universes existed, they left no trace behind. Everything that came before us is erased, making it impossible to recover any knowledge of what happened before our own Big Bang. Another possibility is the idea of the multiverse. Instead of a single universe that cycles through different stages, there may be an infinite number of universes, each with its own beginning, history, and laws of physics. In some versions of this theory, new universes are constantly being born in an ever-expanding cosmic landscape, emerging from quantum fluctuations or bubble-like expansions of space-time. If this is true, then what came before our Big Bang may not have been a single universe, but rather a vast and complex multiverse where every possible reality exists somewhere. But even the multiverse does not fully answer the question of an infinite past. If there are many universes, where did they come from? Has the multiverse always existed? Some scientists propose that time itself may not be fundamental, that what we experience as time is just a human perception of a much deeper reality. If time is an emergent property rather than a fundamental feature of the universe, then the question of before the Big Bang may not have a meaningful answer at all. The universe, in some sense, may simply exist without a beginning or an end. However, there is one problem that remains unresolved: the nature of the Big Bang itself. If we could peer back far enough into the past, beyond even the first few moments of the universe, we might be able to find clues about what came before. But the problem is that physics breaks down at the moment of the Big Bang. The extreme density and energy of the early universe create a singularity, a point where space and time cease to behave normally. This singularity acts like a cosmic curtain, blocking us from seeing anything beyond it. Unless we develop new physics that can describe what happens beyond the singularity, the past before the Big Bang may forever remain a mystery. Despite these challenges, some scientists believe that we may still be able to find indirect evidence of a time before the Big Bang. If the universe is cyclical, there might be subtle imprints of previous universes left behind in the cosmic microwave background, the faint afterglow of the Big Bang. Some researchers have suggested that patterns in this radiation could be remnants of earlier cycles, though so far, no conclusive evidence has been found. Similarly, if the multiverse is real, then tiny distortions in the distribution of galaxies might provide hints that our universe is not alone. But what if we will never truly know the answer? What if the past is lost to us forever, hidden behind an impenetrable wall of cosmic history? If that is the case, then the nature of the infinite past may remain one of the greatest unanswered questions in science. We may live in a universe that erases its own history, leaving us with only the present moment and a mystery that stretches forever into the past. Still, the search for answers continues. Every new discovery brings us closer to understanding the origins of our reality. Perhaps one day, a breakthrough in physics will reveal a deeper truth about time, space, and existence itself. Until then, we are left to wonder, was there something before the Big Bang? Or has the universe, in some form, always been stretching back into an infinite past that we can never truly grasp? The search for intelligent life beyond Earth has long been a question that haunts us. With an estimated 2 trillion galaxies in the observable universe, each filled with billions of stars and countless planets, it seems almost impossible that we are alone. The numbers suggest that life should have arisen many times, evolving intelligence, building civilizations, and reaching out across the stars. And yet, the universe is silent. We have been listening for decades, scanning the sky for signals from alien beings, but we hear nothing. If intelligent life is common, where is everyone? One possibility is that civilizations once existed but are now gone. The universe is ancient, more than 13.8 billion years old, meaning that intelligent species could have evolved and disappeared millions or even billions of years before humans ever existed. If alien civilizations rose and fell long before we developed technology to detect them, then we simply missed them. Their messages, if they sent any, may have passed through our part of the galaxy thousands of years ago, long before we had the means to listen. Or worse, their signals might still be on their way, arriving only after our own civilization has ceased to exist. This idea is a troubling answer to the famous Fermi paradox, which asks why we have not yet encountered extraterrestrial intelligence, despite the overwhelming probability that it should exist. The answer might be simple. Civilizations do not last long. They emerge, thrive, and then destroy themselves before they ever become capable of long-term survival. If true, this means the cosmos is filled with the remnants of once great civilizations, dead worlds, where advanced beings once lived, now reduced to silence. There are many possible reasons why intelligent civilizations might not endure. One of the most widely discussed ideas is the Great Filter, a hypothetical barrier that prevents most, if not all, civilizations from advancing beyond a certain stage. If this filter is behind us, it would mean that life rarely evolves beyond simple microbes, and we are among the first intelligent beings to reach this point. But if the filter lies ahead of us, then it suggests that civilizations like ours inevitably destroy themselves before they reach the level of interstellar expansion. The ways in which a civilization might self-destruct are numerous. Nuclear war is an obvious and terrifying possibility. A species that develops the ability To split the atom gains immense power, but also the ability to wipe itself out in an instant. If alien civilizations had political and social structures similar to ours, then they may have been just as prone to conflict. Wars fought with weapons far beyond our current technology could have left entire planets uninhabitable, extinguishing intelligent life before it had the chance to reach out beyond its homeworld. Another possibility is environmental collapse. A highly advanced civilization may, like us, become dependent on its planet's resources, consuming them at an unsustainable rate. If they failed to manage their technological progress, they may have depleted their ecosystems, altering their climate beyond recovery. Rising temperatures, failing crops, or poisoned atmospheres could have doomed them, leaving their once thriving worlds barren and silent. If civilizations repeatedly destroy their own biospheres before they develop the means to leave their planets, then the galaxy could be filled with dead worlds that once hosted intelligent life. Biological threats could also play a role. A civilization that advances in genetic engineering and synthetic biology might create diseases it cannot control. Pandemics, whether natural or artificial, could wipe out entire populations in a matter of years. If intelligent beings experimented with altering their own biology, perhaps in pursuit of immortality, enhanced intelligence, or artificial evolution, they may have unintentionally engineered their own downfall. But what if civilizations do not destroy themselves intentionally? Some may fall victim to external cosmic threats. Asteroid impacts, supervolcanoes, or gamma-ray bursts could have wiped out alien species before they had the chance to leave their home planets. Even if they became spacefaring, they may have been caught in the path of a catastrophic event, a rogue black hole, a collision between stars, or a supernova explosion. If their survival depended on a single planet or star system, then the destruction of their home could have meant the end of their entire species. There is also the unsettling possibility that some civilizations were not alone, but rather they encountered others who did not have peaceful intentions. If intelligent species are competitive, then the first civilization to develop interstellar travel might have viewed others as threats to be eliminated. The dark forest hypothesis suggests that civilizations remain silent, not because they do not exist, but because they fear attracting attention. If every advanced species assumes that others might be hostile, then the safest course of action is to remain hidden. Those that revealed their presence may have been destroyed before they could ever reach us. If this idea is true, then the universe might not be empty. It might simply be full of civilizations too afraid to speak. Even if some civilizations survive these threats, there is another issue: time. The universe operates on a scale far beyond human comprehension. If an alien civilization flourished 1 billion years ago and lasted for 1 million years before collapsing, that is still an unimaginably long lifespan for a civilization. But in the grand timeline of the cosmos, it would be nothing more than a fleeting moment. If civilizations emerge and disappear on timescales separated by millions or billions of years, then the likelihood of two intelligent species existing at the same time and being close enough to detect each other is incredibly low. We may have simply arrived too late. But perhaps civilizations do not vanish in destruction. Instead, they retreat inward. A sufficiently advanced species may abandon physical exploration altogether. If their technology reaches the point where they can upload their consciousness into machines or create perfect virtual worlds, they may have no need to explore the physical universe. They could have transferred their entire existence into digital space, leaving behind only empty planets and silent cities. If this is the case, then the answer to the Fermi paradox is not that civilizations do not last, but that they evolve beyond what we can recognize. The most haunting possibility, however, is that we are the first. Perhaps intelligent life is so rare that we are among the first beings in the universe to reach this stage. If true, then we are standing at a precipice, facing a choice that has determined the fate of all those who came before us, if they existed at all. We have the potential to become the first civilization to break free from the Great Filter, to survive beyond our own planet and spread across the stars. But we also face the same dangers that may have doomed countless others. The silence of the cosmos is not just a mystery, it is a warning. If civilizations before us have destroyed themselves, then we must learn from their mistakes. If the universe is truly empty, then the responsibility falls on us to ensure that intelligence does not end with humanity. We have the ability to shape our future, to decide whether we will be just another lost civilization or the first to endure. For now, we continue to search. We listen for signals, send our own messages into the void, and hope that we are not too late. Perhaps one day, we will hear something, a whisper from a distant star, a trace of a civilization that survived where others failed. Until then, we are left with a great silence, wondering whether it is the echo of those who came before us, or the absence of anyone at all. The fate of the universe is one of the most profound mysteries in cosmology. We exist in a universe that had a beginning, but what happens at the end? Will everything collapse in on itself, tear apart into oblivion, or simply fade into nothingness? No matter which scenario plays out, there will be a final horizon, a point in the distant future where no observer, no matter how advanced, will ever witness what comes next. The end of the universe will not just be lost to us, but to all of existence itself. To understand the future, we must first look at the past. The universe began with the Big Bang, an event that marked the creation of time and space itself. From an unimaginably small and hot point, everything expanded outward, forming galaxies, stars, and planets. But the force that set the universe in motion, expansion, has never stopped. For billions of years, gravity shaped the cosmos, pulling matter together into vast structures, while an invisible force called dark energy worked against it, pushing space apart. Today, we know that dark energy is winning. The universe is expanding faster than ever, and as time goes on, galaxies will drift farther apart. What we see in the night sky today will look drastically different in the distant future. Eventually, Entire galaxies will disappear from view, slipping beyond the cosmic event horizon, forever unreachable, their light never able to reach us again. This alone is a terrifying thought. One by one, the universe is erasing itself from our perspective. But the true fate of the universe depends on how this expansion continues. Scientists have theorized several possible endings, each more haunting than the last. One of the most dramatic is the Big Rip. If dark energy becomes stronger over time, it will not only push galaxies apart, it will rip everything apart. First, galaxy clusters will dissolve, then individual galaxies will break apart, leaving stars stranded in the void. Planets will be torn from their orbits, left to wander through an increasingly unstable reality. Eventually, the force holding atoms together will fail, and in the final moments, everything, matter, space, even time itself, will be ripped apart at the most fundamental level. The universe will not just end, it will be violently destroyed at every scale. But there is another, quieter fate, heat death, also known as the Big Freeze. In this scenario, expansion continues, but at a steady rate, eventually spreading all matter so far apart that nothing can interact. Stars will exhaust their fuel and fade into darkness. Black holes, the last remaining structures, will slowly evaporate over trillions of years. In the end, the universe will be cold, empty, and lifeless. No new stars will form, no galaxies will collide. There will be no motion, no warmth, no change. The universe will not explode or collapse. It will simply stop doing anything. This is the most haunting idea of all. Not a fiery cataclysm, but a slow, inevitable fading into nothingness. And the worst part? No one will be left to witness it. If any civilizations exist billions or trillions of years from now, they will slowly fade with the stars. The last conscious being in the universe will have no one to tell their story to, no one to hear their final words. When the last source of energy is used up, existence itself will go silent. But there is still one more possibility, one that offers the tiniest glimmer of hope. Some theories suggest that the universe is cyclical, meaning that after the universe fades or rips apart, a new one could be born. If this is true, then the end is not truly the end, but the beginning of something new. However, if a new universe is born, it will be completely disconnected from ours. There will be no way to remember what came before, no trace of the past left behind. Our universe, everything we know, everything we have ever been, will still be lost forever. No matter what happens, the final horizon of the universe is a line no one will ever cross. The end will come, and there will be nothing left to see it. The universe is an endless expanse of wonder, filled with mysteries that stretch beyond time itself. It calls to us, igniting our curiosity and ambition, urging us to explore the unknown. And yet, as much as we dream of reaching the stars, there are places in this vast cosmos that we will never set foot in, regions so distant, so hidden, or so fundamentally unreachable that they will remain forever beyond our grasp. These are the forbidden zones of the universe, and no amount of technology, ingenuity, or perseverance will ever allow us to breach them. Some of these places are lost to the relentless expansion of space itself. With each passing moment, entire galaxies race away from us at speeds faster than light, carried by the ever-growing fabric of the cosmos. The deeper we look into space, the more we realize how much is already gone. Regions that were once within reach now exist beyond a point we can never cross. Even if we somehow developed engines that could propel us at the speed of light, it wouldn't be enough. Even closer to home, the barriers of the universe are insurmountable. Black holes, the most enigmatic objects in existence, hold secrets we may never uncover. Their event horizons are more than just a boundary. They are a one-way door to oblivion. Anything that crosses it, no matter how advanced, no matter how powerful, will never return. Not even light can escape, and whatever information falls inside is effectively erased from the universe as we know it. The very nature of space and time within a black hole is unknown to us, perhaps unknowable. If we could somehow send a probe into one, its signals would never reach us. If an astronaut ventured too close, they would be stretched and crushed into nothingness before their story could ever be told. The heart of a black hole is not just forbidden, it is the ultimate point of no return. And what about the true beginning of everything? The moments after the Big Bang hold answers that could explain our entire existence, yet they are locked away behind a veil of physics we cannot penetrate. The universe, in its infancy, was so hot and dense that light itself was unable to travel freely, meaning no telescope, no matter how powerful, can ever show us what truly happened at the very start. The first moments of time itself exist behind an impenetrable wall, a forbidden zone not in space, but in time. But perhaps the most unsettling reality is not just that there are places we can never reach, but that their numbers are growing. Every second, new regions of space drift beyond our ability to ever explore. The universe is expanding, and with it, the possibilities for exploration are shrinking. 1 trillion years from now, there will come a time when our own Milky Way is the only thing visible in the night sky. Every other galaxy will have vanished beyond the cosmic horizon, never to be seen again. Future civilizations, no matter how advanced, will never know of the vast cosmos we can still glimpse today. To them, the universe will appear as a lonely, isolated island in an infinite void. Yet, despite knowing all of this, we continue to reach, to wonder, to dream. Even if we can never set foot in these lost places, even if the universe has set limits we can never cross, our desire to understand is limitless. Perhaps that is what truly defines us, not where we can go, but what we seek to know. The forbidden zones of the universe may never be explored in person, but they will always be explored in our minds. And in that sense, the journey never truly ends.